Okay, hey, welcome back. This is Calc 1, and we're going to deal with the Riemann sum today and the definite integral. So first, some definitions. Before, when we dealt with the sums for finding area underneath a curve, what were we doing? We're taking the limit of the sum of f of x sub I times change in x sub I. Okay. And in order to do this, I maybe not noted it, but you would need a continuity of f of x on whatever interval you're working on. Oops, and there I kind of already alluded to what's going to change here in the big way. The change in x that we were working with always has to be, always had to be b minus a over n. Okay. There was a third thing that I also probably didn't note. F of x had to be above the x-axis, or f of x had to be non-negative. Okay, so now in this definition, those three things are sort of thrown to the wayside a little bit. Continuity is something we'll kind of usually assume for integrability, but for right now, we just want the function to be defined, and then we'll redefine change in x to be more variable, looser, if you will, and we'll allow f to be negative if we need to. Okay, so anyways, let's get to the definition. We'll say let f be defined. And you know, what are we doing right now? We're getting a new one of these things, a new sum. Okay, so let f be defined on this closed interval from a to b, and let delta be a partition of the interval, the closed interval from a to b, given by, in this case, a equals x sub 0 less than x sub 1, so less than x sub 2, blah, 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 x sub n minus 1 less than x sub n, which equals b. Okay, this is kind of, you know, before when we were working with area, what that is, what the partition is just basically how we sectioned up this interval. And before we were doing it real easily with these equidistant subintervals b minus a over n. But now we're saying we can choose our endpoints pretty much any way you want. Okay, and then our delta x sub I will be defined by the difference between two consecutive endpoints. Okay, so x sub I minus x sub I minus 1. So given any point in the subinterval, so given any, we'll call it c sub I in the interval from x sub I minus 1 to x sub I, now we'll have the definition for the Riemann sum. We have the sum of f of c sub I times change in x sub I from I equals 1 to n. That thing is your Riemann sum. So we have the sum, blah, 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 which is called, make sure my English makes some sense here, which is called the Riemann sum. Okay, great. The problem here with this definition is before our limits were kind of, I guess, dependent on just letting n go to infinity. Here we're going to say let the partition go to 0. Let the greatest width of the partitions, which we're going to call the norm of the partition, go to 0. So I guess I need to define that. Also note the norm of the partition, which equals the width of the largest subinterval. So you're going to see that when we deal with our limits. And for the most part, we'll just kind of sweep that under the rug and just deal with the limit of the sum as n goes to infinity. For the cases where you have equidistant intervals, like the change in x equals b minus a over n, those two limits are pretty much the same. So usually for us, saying the limit as the change, the norm of the partition goes to 0 of the sum of this f of c sub I, change in x sub I, will be the same thing as just taking the limit as n goes to infinity of that thing. Okay, so it's kind of a non-issue right now, and we'll kind of treat it as such. Anyways, let's take a look at an example. Given our f of x equals the square root of x, evaluate the limit as n goes to infinity of the sum of f of c sub I times change in x sub I, I equals 1 to n, where our sort of endpoints of our intervals are given by I squared all over n squared, and we want to use the right endpoint for the interval 0 less than or equal to x less than or equal to 1. Okay, so what's weird about this one, what's different now is the widths of these intervals. So a visual picture kind of helps. So maybe a sub-example here with n equals 4, and in that case c sub 1 would be 1 over 16, c sub 2 will be 4 over 16, c sub 3 is 9 over 16, c sub 4 is 16 over 16, and what does the picture look like in that case then? Start at 0, go to 1. It's a square root function, so it's concave down. And so here's 1/2, 1/4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. Okay, so the first rectangle that we're sort of figuring out the area for is at 1/16. So it's right there, really small. Then 4/16 is right here. And then 9/16 is right here. So you see the widths, the long story short, the widths of the rectangles are not all the same now. And then 16/16, there's our last rectangle. Okay, great. So we want to actually do the limit of it. In order to figure out the limit of it, I need to kind of get some things straight. I need this thing right here for the computations. So I'm going to go ahead and figure that out just to the side. I mean, you would have been forced to eventually. I've done this problem enough times, and I know I'm going to need that, and it's a pain in the butt. So let's go ahead and get that. So what do we have? X sub I, or in this case, C sub I minus C sub I minus 1. So that's just I squared all over n squared minus I minus 1 squared all over n squared. So what do I get? I squared minus 2i plus 1 all over n squared. And if you simplify, change in x sub I will become, these are canceled, 2i minus 1 over n squared. Okay, so we want to figure out then the limit as n goes to infinity of the sum of f of c sub I, and c sub I is just I squared over n squared, times change in x sub I, which we just evaluated to be 2i minus 1 over n squared. And then we want to go, and I equals 1 to n. Okay, so once you get it in this form, it's just like doing the work in the previous section. You're going to plug the I squared over n squared into the function. Okay, so you would end up with the square root of I squared over n squared times the 2i minus 1 over n squared. And then that'll equal the limit of the sum of I squared over n squared times 2i minus 1 over n squared. And then that'll just be the limit of the sum of 2i cubed minus I squared over n to the whoops, when I took the square root, that's 2 should have went away there. So it's just all over n cubed. Over n cubed, and then we could split up that sum and use our formulas for sums from the previous section to simplify parts. So this would be 2i cubed over n cubed minus the sum of I squared over n cubed. Then you could factor out the stuff that's not dependent on I. So you'd get the limit of the sum. Oh, and I saw another mistake. When I did not take the square root, right? Right there, sorry. So the square root of I squared over n squared is just I over n. That's what I've been screwing up. So this would be just, this would be, this is 2i squared then minus I. So then this would be I squared. And then the other guy is just an I. Okay, so anyways, again, like I said, factor out the non-I material. So 2 over n cubed times the sum of I squared, sorry, minus 1 all over n cubed times the sum of just I. Okay, and then using our formulas, this would be 2 over n cubed times, what do we have, n times n plus 1 times 2n plus 1 all over 6 minus 1 over n cubed times n plus 1 all over 2. And we're taking the limit as n goes to infinity. So this first limit, the high degree stuff, is what all we really care about. So again, let's multiply 2n, n, and 2n. On the other side, it's n times n. So our limits become, limit as n goes to infinity, of 2 times n times 2n. So that would be 4n cubed all over 6n cubed. And minus n squared all over 2n cubed. Okay, and then we can simplify those to infinity. 4, 6 minus 1 all over 2n. And of course, the second term will just go to 0. You'll be left with 4, 6, which is 2/3. Okay. So, I mean, I guess it's a more general type of sum that we're using. And we can apply it to more stuff. And if you kept taking math, that's kind of what you would go and chase after, are these weird nefarious type functions where they have parts that are not continuous, and then you have questions like, well, can I take the integral of something with a finite number of discontinuities? Can I take an integral of something with an infinite number of discontinuities? Are there other ways to build integrals? And yeah, there are. There's something called a Lebesgue integral. One of my teachers told me in the 70s that everybody had their own integral, and you would go to math conferences and just listen to people present their own versions of integrals. So it's the waters run deep. Okay. So anyways, now that we have this Riemann sum definition, we can define what is called the definite integral. Okay. Section 2, the definite integral. So basically, if f is defined on an interval from a to b, and we have this limit which exists ultimately, so the limit as the norm goes to 0 of the Riemann sum, so if that thing exists, then the limit is going to be the indefinite integral, and it will be notated with this integral symbol again, f of x dx. At this point, though, we haven't really made it clear that the connection between the area problem and the antiderivative problem. So they'll even say it in the book, like in the footnotes somewhere, that the notation is the same. So if you remember in 5.1, we have the notation for f of x dx for this was called the indefinite integral. And all that was giving you the antiderivative. Okay. So for example, the integral of x squared dx, the indefinite integral would give you x cubed over 3 plus c. Okay. The point I'm trying to make is that although the symbols now are kind of lining up, we haven't really lined up the connection between area underneath the curve and the antiderivative. Okay. It's not there yet. We're getting closer. Okay. Okay. So anyways, this thing, you kind of think of it as separate for right now, but then we'll make it all come together here in one more section. Okay, so anyways, this thing is called the indefinite integral. Or sorry, the definite integral. The big difference is it outputs a number as opposed to outputting an antiderivative. So it's called an indefinite integral from a to b. B is called the upper limit. A is the lower limit. And I'm sure I said this before, sort of off to the side, but in general, if f is continuous, then we're going to be able to get the definite integral. So if f is continuous, then we can find its definite integral. Okay. So continuity is a super serious, super powerful kind of property, and in general, we'll be dealing with functions that are continuous. Okay. Okay. Let's apply this to a problem from the book. It used to be number 4. It's not anymore. We'll just write it as an example. I want to find the I want to find the definite. And how many times am I going to screw that up, right? I'm going to find the definite integral going from -2 to 3. Okay. The picture, we can draw the picture real quick. So -1, 2, 1, 2, 3 looks like this. So 1, 2, 1, 2, 3. Okay. And usually if the function is positive, we could say that we're finding the area underneath the curve. And what's weird with this thing is this other side. How do you find the area underneath that? You know, so is the definite integral going to find that area, or is it going to? I mean, you can kind of think it out if you think in terms of the rectangles. The rectangles over here will all have negative f of x's for heights. They'll all have negative heights. So when you add them all up, you should get something negative for this. And then for this region, you should get something positive. Okay. In the end, what happens then? Well, the indefinite integral will probably be the sum of the negative of the area of this first kind of triangle. I guess maybe put it in red or something. So the area of that triangle, 1/2 base times height is 1/2 times 2 times the height is 2. So that'll be 4 times 1/2, which is 2. And then the other rectangle, maybe put it in blue or something, over here, area of the other triangle, 1/2 base times height is 9/2. halves. What I expect then from just what I know about Riemann sums and how we're adding up rectangles and how literally it's the sum of f of x dx. Those f of x things are going to be negative on that red side. It's going to be the difference of those two, right? So what I'm saying is that the sum from the definite integrals, from negative 2 to 3 of x dx, I'm expecting that to be 9 halves minus 2, which is the same as 4 halves, which is 5 halves. Okay, so rather than just strictly giving you area, that's why we had to have like the additional requirement that the function we were figuring out had to be non-negative back here. Okay, so if it does go negative, then you're thinking of a difference going on, okay? Because your one region is going to be okay. So I'll show up. Let's just go ahead and do this. Right. So I'm going to use the techniques from the previous section. I'm going to use the right endpoints. So it's the limit, and I can use n going to infinity instead of the partition going to 0 because I'm using the change in x as b minus a over n. So let's get the change in x while we're at it. Change in x is 3 minus negative 2 over n, which is 5 over n, I believe. So we have the sum of f of, and I'm going to use the right endpoints. So for my right endpoints, the x sub i's, I guess, will be a plus change in x plus I minus 1 times change in x, which is negative 2. The change in x's will cancel, plus I change in x, where change in x is 5 over n. Okay. So f of negative 2 plus 5i over n, and then times the change in x, which is 5 over n, n equals 1 to, or I equals 1 to n, sorry. Okay, and then we just need to compute that. Evaluating is pretty easy. Clearly, just plugging negative 2 plus 5i over n into x gives you negative 2 plus 5i over n, n times 5 over n. I'm going to start, so I have to distribute this guy and then split up the summation. So negative 10 over n plus 25i over n squared. And then that'll be the limit of the sum. And I can factor out anything not dependent on I. So negative 10 over n, sum of 1, I guess, plus I can factor out the 25 over n squared, sum of I. And then that'll equal the limit of negative 10 over n times n plus 25 over n squared times n plus 1 all over 2. And so we get negative 10 times n, so we have a limit of basically negative 10 plus, and then up top it's basically n squared, right? 25n squared over 2n squared. Just leave me at 25 over 2. And then the limit of a constant is a constant. So we have negative 20 halves plus 25 halves, which of course is the 5 halves that I predicted. Okay, so if you're just worried strictly about finding area underneath the curve, you can't really use these things if your function's non-negative. Okay, so there's a theorem in the book then, theorem 5.5. Basically, if f is continuous and non-negative on the interval from a to b, then you can use this definite integral to figure out the area. Okay, so then basically the area underneath this curve, whatever it is, so long as it's continuous, blah, 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 that area is just equal to the definite integral from a to b of f of x dx. Okay, so the area is equal to that. Okay. So ultimately then, if you get a really nasty integral and you're not sure how to do it, you can use just what you know about geometry to evaluate the integral. So in particular, if you have maybe something nasty looking like absolute value and you don't know how to deal with it, so let's say 1 minus the absolute value of x from -1 to 1, you could graph the picture and figure out the area underneath the curve, so long as the curve isn't going negative. But even if it's going negative, from the trick I just showed you, just make the area negative and add it to, I mean, you can still figure it out. Anyways, the graph of absolute value of x is like this, and then negative absolute value of x flips it around the x-axis, and then 1 minus absolute value of x will shift it up 1. Okay, so our graph, is going to look like this. We want to find the area underneath it from -1 to 1, so we're just looking for the area of this triangle. That's easy, that's 1/2 base times height. So the base is the length of the base, 1 minus -1, times its height, which is just 1. So 1/2 times 2 times 1, so it's just 1. Okay, another one. So this one always kind of confuses people, and you'll see it again and again in the calculus books. It's basically variations of this thing. Okay. What the heck is that integral? Well, look at the insides. So the guts of it, y equals the square root of r squared minus x squared, the integrand, as they call it. You can square both sides, you get r squared minus x squared. And then bring the x squared over, x squared, oh, it's a circle, right? It's the upper hemisphere of a circle. Okay. So radius r, so -r to r, and the insides there represent a circle. And so that integral, because this thing is positive and continuous, represents the area underneath that curve from -r to r, which is, from geometry, we know the area of a full circle is pi r squared. The area of half the circle is 1/2 pi r squared. And literally that is your answer. It's not until Calc 2 that you can actually figure this out by hand. You won't even learn how to do it in Calc 1. You would have to use geometry. Okay, some other miscellaneous properties of integrals, which I'm not going to get carried away with. Props of integrals. First off, the integral from a to a of f of x dx. Now there's other kinds of integrals. So the Lebesgue integral, there's a Riemann-Stiglitz integral. Those are the two that I remember from grad school, but I don't think we studied any other ones. So anyways, this thing kind of asks how much area is underneath a point, right, at A, and we'll just presume there's no area underneath it. Okay, so we'll just say that's equal to 0. The integral from a to b of f of x dx. You could flip kind of the integral and make it from b to a, but you have to change it negative. Okay. Thirdly, you can split integrals. So a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. What else can we do? You can, of course, factor out constants. So the integral from a to b of a constant times f of x dx is just k times the integral of f of x dx from a to b. Of course, the sum and difference of the definite integral of a sum or difference of functions is equal to the sum of the definite integrals. Okay. So we saw that with the indefinite version, just like number 4 we saw with the indefinite version as well, but it also holds with the definite integral. What else? Some working with inequality statements. You can basically, it'll come down to the idea, you can basically take the integral of both sides of an inequality, so long as it's the weak inequality, that'll work. If f of x is greater than or equal to 0 on your interval from a to b, then you could take the integral on both sides, the definite integral. The integral from a to b of f of x dx will be greater than or equal to the integral of 0, which is actually just 0. And then likewise, if you have a function f of x greater than or equal to some other function g of x on the interval from a to b, then the integral, you can take the integral on both sides and it'll still be a true statement. Okay, so from a to b, then we have this statement is true. A to b, g of x dx. I don't know if that holds for the other types of inequalities, but at least you'll have this factoid in your toolbox. And yeah, so a lot of stuff there. And some of it's pretty theoretical, like in the beginning, all that stuff, but all we're doing is trying to connect the bridge between the idea of the antiderivative and the area problem. Okay, so we have these two kind of competing issues at this point, and in the next section we'll see how to connect them using the fundamental theorem of calculus, and then ultimately there's a big connection then even seen in the notation, as you see here, between the area, finding the area underneath the curve, and finding the antiderivative type thing. Okay, I don't know. It's all very interesting. And thank you for watching, and we'll see you next time.